Good morning, class, and welcome to this lesson on Electrostatics 13, energy in a capacitor. Today, we will be able to derive the two equations for energy in a capacitor. So, as you can probably imagine, with a capacitor, we are storing charge. We are storing charge on these plates. And because we are storing charge on these plates, these charges have the potential, these have the potential to move. Just like in the camera example I gave you earlier, if we are able to connect these two plates in a different manner, these charges will be released and they will actually power something up. So they have a potential, or in essence, when charges are stored, they have energy. And since everything in physics comes back to energy in almost every single topic, how much energy does it have? Um, we're going to do that here as well. So let's go back to one of our original equations in this chapter. Energy is the product of charge times the voltage, or work is the product of charge times the voltage. Remember, energy and work are the same thing. Okay, energy and work are the same thing. Well, in a capacitor, we know that the equation is Q equals C times V. Q equals C times V. We know C is a constant, and we know that Q and V are both directly related. So as Q goes up, V goes up. And so if we graph this, a plot of Q versus V, when Q goes up, V goes up. And so we would get a nice straight line like this. Well, energy is equal to the product of Q times V. So on a graph, when we ever multiply the two axes, whenever we multiply the two axes, what we are doing is we are taking the area under the curve. Okay, we're taking the area under the curve. And as you can see, this is a triangle. So energy in a capacitor, one of our first equation right here, energy in a capacitor is equal to 1 half Q times V. 1 half Q times V, based off this graph right here. Charge goes up, voltage goes up, they're directly related, we're going to have a nice straight line. Because of this straight line, and because of this equation, Q times V, we're taking the area under the curve. And the area under this curve, which is a triangle, is going to be equal to 1 half Q times V. Okay, so that's our first equation. Notice there's no capacitor in this equation. The value C is not in here. Okay, so we get our second equation because we know that Q equals C times V. Okay, we get that right up here. Q equals C times V. And so if we want to relate it, we can plug this into here. So we get U equals 1 half C times V times V. Or we get energy in a capacitor is equal to 1 half C V squared. Okay, so these are our two equations for energy in a capacitor. And both these equations are going to give us an answer in joules, okay, standard units.